Hi, I am Guillermo Betancourt, and I am going to present my argumentative exam. In the first situation, we have a Biot-Savart law, which we know the formula. Then we have a current carrying wire and a square loop, and we have a test point in here. We know that the differential in length is equal to the set d set in the set the direction, and we know that the radius is rho, and is the perpendicular distance from the source to the test point, and it is going in the direction of rho. We know that the separation vector is r, which is the separation vector from the source to the test point. And then we are going to calculate r, knowing that dl is the differential of set in the direction of set, and that r vector is equal to rho in the direction of rho minus set in the direction of set. We can substitute in this equation. Now we are going to calculate the cross product between dl and r. With this, we are given the direction of the magnetic field in direction of phi, which we know is in the positive set, in differential set. And now we use trigonometric substitution technique. We know that cot is equal to set over rho. Then we solve for set, and we derivate this. Well, there are some things like that we know from our tables, like these three formulas. With these things that we know about our tables, we can integrate this formula, this equation, and we are given this final expression. But we have a cos of alpha 2 minus cos of alpha 1. So now we are going to get these two things. We're going to study alpha 2 and alpha 1 in the magnetic field. For this, we're going to use law of cosines. Um, Using law of cosines, we end up with this final formula where we obtain like a new value of cos of alpha 2 and cos of alpha 1. In our situation two, we have a magnetic field due to a circular loop in the x-z plane. So first, I draw a graph where we can see this circular loop in the x-z plane with the current flowing from the positive z to the positive x. We're given 2 points, 1 point in the positive y and 1 point in the negative y. I'm sorry. Now we know that the differential of length is going in negative phi direction. And now I have a graph of the top view from the y-axis, where we can see the differential of phi, the differential of length. Well, in this case, we know that the differential of length is equal to rho differential of phi in the direction of phi. So in the first point, we know that some point in the current is have the value of x, 0, and z. Also, we know that there is a radius, in this case rho, which value is rho in the direction of rho. Our point on positive y is equal to 0, h, and 0. With these two things, we can take the separation vector, which is r. Once we calculated r, we know that we can substitute phi differential, no, phi in the direction of, I'm sorry, we can substitute rho in the direction of rho because we know that that is equal to x and z because it is only in the x and z plane. With this, we are going to have this final expression of R. So now we can do the cross product. The cross product gives the direction of the vector field, which in this case we know that it only have components in direction of rho and direction of y. And well, due to the high symmetry, we can cancel x and z components of the direction vector. So in the formula, we must only get y components of the dl cross product with r direction. And this means that the Biot-Savart law, the H is only going to have components on y, on the y direction. So back to this integral, we have to substitute dl cross product with r. Um, and then we solve it, and we know that this is not equal to zero, so we know that this integral cancels out. Now, for only for proof this, we get the absolute value of this direction of rho, and we know that this is one, so we confirms our integral that cancels out. The Biot-Savart law, I repeat, we only have components in y. So now we have our graph when we can show that these x components cancel out, and we only have left with y components because of this high symmetry. So now in our final expression for this first point in this positive y, we know that this is the direction. So now we are going to do the same, but with the point in the negative way. So it's the same process. The only thing is that is in the negative y direction, but is the same magnitude. We also know that these x components cancel out due to the high symmetry, and we only have one vector going the negative. And with this formula and with this right-hand rule, we know that magnitude in these both fields, both points, is the same, but they have opposite directions. So now in the situation three, we have a magnetic field due to an infinite current sheet, and we are going to make use of the Ampere laws. So we have the current sheet only in the Z and Y plane. We have our point in positive X. So now we're going to analyze the wire on 0, comma y, comma 0. Um, so now from a top view, from this X, we are having this graph where we can solve two magnetic fields with their directions. Uh, at this, as the point that we're going to evaluate, which is the point on the X, we know that these are the behaviors of the direction of the magnetic fields. So with this, we can interpret that there is only going to be este, like a sum of these two vectors with a direction in only the positive y. So now we're going to analyze this with the Ampere's law, um, and we're going to use the Ampere's trajectory. For this, we're going to label first our square with this side A, this side B, and points 1, 2, 3, and 4. And then we're going to split our integral into 4. At first, we're going to evaluate the segment 1 to 2. I'm going to tell that all segments have the same B, which is the magnetic field, which we obtained before, which is going to be the magnetic field in direction of Y. So it's the same for all the 4 segments. So in segment 1 to 2, we know the magnetic field, so the differential of length. We can saw it here is this part. So we know that it is on the differential of x in the x direction, which this we can make the dot product. And because of the vector y and the vector x are perpendicular, this is going to be 0. Now for the segment 2 to 3, we know magnetic field is the same. Differential of length is on the y direction, as we can see here. And, and then we know that cos of 0 is equal to 1. So we're only left with this expression. So it's the same process from for segment 3 to 4, but then we only know that the differential of x is going in the negative x. But this doesn't affect too much because we know that the vector of y with the dot product of the vector of x is equal to 0. Segment 4 to 1, it's the same. Differential of y in the negative y direction. And we know that cos of 0 is equal to 1. So we are left with this negative expression. Then we are going to add all our segments, integral segments, and we evaluate them, and we are only left with this, but we know that this is equal to the current, so now we can only solve for the magnetic field, and this expression is the intensity of the magnetic field. Also, we know that the length is equal to the B in our diagram here. So, um, also we know that the current density is equal to current over the V, which is the length. So now we can substitute the K into here. And finally, we got that magnetic field is equal to K over 2 in the direction of Y. But also, because of the symmetry, this field is parallel to y-axis and constant in magnitude to either side of the sheet. The infinite sheet means the field does not depend on x or z, only on the sign of y of x. I'm sorry. And well, if we apply the right hand rule with fingers in direction of current minus z, the thumb shows us the direction of the magnetic field in the y direction. The situation for is the motion of a charged particle in a magnetic field. We know that magnetic field is going to negative y direction. We know Lorentz formula and initial conditions, t times seconds. In the position, initial position is 0, 0, 0. And we know that we only have a vector in of velocity, the negative. So first, we know the Lorentz force with an electric field of 0. We know that this of force obeys this Newton's second law, which is force is equal to mass times acceleration. So now we equal this Newton's second law with the Lorentz force. We know that the acceleration is the differential of volume of velocity over time. I'm sorry. So now we can only solve for A, and then we can change this A. We can substitute this A for these all differentials of velocity in each of the x, y, and z components, which we have an acceleration vector. And now to calculate the cross product between velocity and magnetic field, um, we are only left with this expression, which now we can substitute in our previous formula. And we are left with this, which is the arc vector, and this, which is a vector. So now we're going to match the corresponding components from both sides. Um, and we get a system of differential equations of Bx, By, and Bz. So now, um, doing this process, we are left with this, which we know that we can substitute from this previous one that we had before. So we substitute, and then we get an ordinary differential equation, linear, with constant coefficients and second order. And using table, the solution is as follows. From before, we know these two things. So now I can substitute Bx into this, which you can see. We are left with this Bz. So now we have all these three components of the velocity on the x, y, and z. And then a very important thing is to determine A, B, and C. So we are going to make use of our initial conditions. So we are going to put all our velocities at time zero. Uh, from this, we know that A is equal to zero, C is equal to zero, and B is left with minus initial velocity. So finally, we can substitute our A, C, and B values on our final velocity uh, from our three X, Y, and Z. Now we can get the acceleration by only making this derivative of velocity. We are left with these three. And now for getting this position vector, we're going to integrate velocity. So we do our process, and these are our final positions on X, Y, and Z. So now let's discuss periodicity. We know that these two are equal. We know the values of amplitude, angular frequency, phase, and time. We know this formula of period, and we also know the angular frequency. We only have to substitute, and we are given this final equation. So now, This period means that the motion in X and Z is periodic, since there is no force on the Y motion, and the motion is a helix. The magnetic field bends the particle into a circle in the XZ plane. So now let's discuss trajectory and geometry. It's an helix particle. The particle moves in a circular path on the XZ plane while drifting linearly along the negative x-axis. Due to the constant By is equal to minus B in zero. These are the graph of our position components in the X, Y, and Z, velocity components, and the acceleration components. For the situation 5, magnetic force on a current carrying loop due to a long straight wire. First, we have our diagram. We can see the infinite wire, which is carrying a current 1. We label these three segments, which are 1, 2, 3, and 4, and the respective differential of length. We know that this is a magnetic field caused by the infinite wire. So now we know that this is the total magnetic force in each of our points, 1, 2, 3, and 4. And this is the formula of electric current. So now using these two things, we are going to separate our total magnetic force into four. First, we are going to analyze this, D1. We know that we have a differential offset. DL is a differential offset. And going in the Z direction. And we are going to evaluate this from H, which is in the top, to 0. And then we know that cross product between these two vectors is equal to a negative because of this. And then we are only left, we evaluate our integral, and we are only left with this. The same process is here for the second part, where we are now know that the differential of length is a differential of rho, the direction of rho. So we can see here the second point. We know that we are going to evaluate from initial rho to initial rho plus the width of this rectangle. So now also we know that the cross product between these the vector rho and vector phi is equal to z because of this. Then we only evaluate our integral, solve it, and we are left with this expression. The same here. From the third part, we know we are going to evaluate this direct differential offset from 0 to h. Cross product between these two vectors is equal to negative vector rho. We evaluate this integral with the set. We are left with this equation. So now, same here, evaluate differential of rho, the last point. Now we are going to evaluate from initial rho plus y to rho, to initial rho. Then we know the cross product between the vectors is equal to the to the vector in Z, and it's positive. Now we are left with this expression, but to change the order of these two denominator and numerator, we only put a negative sign, and we are going to build to to have this final negative expression. Finally, we are going to add all our forces. We know that force 2 and force 1 cancel each other out. So now we're going to add only force 1 and force 3. We are left with this in the direction of rho, and this direction represents the repulsion against the wire. And we notice that the absolute value of the force in point 1 is greater than the absolute value of force in point 3. This is because of the denominators of rho and rho plus y. Uh, at last, we have this diagram where we can show that all four forces are going to the like are going to into this square loop instead of going outside. The net torque on the rectangular loop is produced by the vertical sides of the loop, which is parallel to a current carrying wire, and these segments carry currents in opposite directions along the z-axis and are located at different distances from the wire. So they experience magnetic fields. Out of the magnetic forces, these segments point on the opposite y directions. Their magnitudes are unequal due to varying magnetic field. This imbalance creates a net torque that tends to rotate the loop about the x-axis, which is perpendicular to the x-z plane. Situation 5, we have the Lorentz force law, where we know the electric is equal to E zero in the y direction. Well, we have these conditions. Now we're going to do the magnetic force calculation, where we're going to do this cross product. We're left with the initial velocity, then the initial magnetic field are negative and in the y direction. And then the magnetic force is equal to this, and the electric force calculation is this. So the net force condition for the velocity to remain constant is these two equal to zero. Then we only simplify and solve for initial magnetic field. We are left with this. In the alternative scenario, the Lorentz force is going to be equal to zero. For this alternative scenario, we have these conditions. So now with this, we are going to do also a cross product, which left us with this. So now we're going to put the x components in here and the y components in here, and we're going to solve for the velocity in y and velocity in x. Velocity in y is equal to zero, and velocity in x, we know that is this expression that is left. So now this is our final result with our diagram, where we know that velocity is going in the x direction, magnetic field is going in the z, the electric field is going to on the y. We know that electric force is going on y. We know that magnetic force equal to negative y with this diagram. And then when the electric is equal to electric, when E0 is equal to V0, magnetic field zero, the forces cancel and the particle moves straight. And in the conceptual analysis, This setup is a velocity filter and it only left particles, lets particles with exact speed um, equal to the speed that we with this pass straight to faster or slower particles get pushed off uh, of this course. This is useful in machines that need to sort particles by speed, like mass spectrometers. And this is my final situation 7 MATLAB code. Um, I run the code, and this is the result. And well, this MATLAB code calculates the magnetic force acting on a straight wire segment carrying an electric current with a constant magnetic field. And it defines the coordinates of 4 points A, B, C, and D, forming a closed path. And the user selects one of the segments AB, BC, CD, or TA based on the select segment. The length vector L is computed by subtracting the coordinates of the segment endpoints. And then the magnetic force is calculated using the formula force is equal to current times the cross product between length and magnetic field, where I is the current, B is the magnetic field, and the result is displayed in the console.